So today we're going to learn about what's called a first-order linear differential equation. And so first of all, we need to recognize them, right? A first-order linear differential equation is going to look like this. Y prime plus p of xy equals q of x. Now, I don't really want us to just memorize that thing. I want us to sort of effectively understand what this is and why it's called this. And so there really are two parts to that. There's the words first order and there's the word linear. And so, we're going to sort of look at what is it about this differential equation that makes it first order and what is it that makes it linear. So first of all, first order. When we say that a differential equation is first order, it means that the highest derivative in that differential equation is a first derivative. So as you look at this expression here, we can see that the highest derivative in this is first degree or first order, which means this is a first order differential equation. If this had a y double prime plus on the front of it, it would be a second order differential equation, but it doesn't, and so this is a first order differential equation. Second, linear. When we say that a differential equation is linear, what it means is that the variables, and by the variables, I mean the y variables, right? So when we say that it's linear, it means that those variables are only raised to a zero power or to a first power. So for instance, if you had a differential equation like this that had a y squared in it, or on the other side had a plus y cubed in it, or had like a minus sine y in it, these would all not be linear differential equations. Now, of course, we're not dealing with that. We're going to be dealing with this. We're doing first order linear differential equations. And notably, this thing is going to be sort of our standard form for this first order linear differential equation. Now, as we start moving forward into how to solve these things, there's this really, really important term, and that's an integrating factor. It turns out the concept of an integrating factor is something that's going to come up a lot in your future studies of differential equations, and this is the first order linear differential equations is going to be the first place where we start to learn about an integrating factor. And integrating factors really don't need to be super complicated. An integrating factor, like at its essence, is really nothing more than something you multiply through a differential equation that makes that equation simpler to solve. And so as we go through how to solve this problem, you're going to get a chance to see why this integrating factor helps. Now, in the study of differential equations, there are lots and lots and lots of different ways to get integrating factors. And so for today, we're just going to be talking about integrating factors for first-order linear differential equations. And as you can see on the slide here, this entire lesson hinges around this key point. Like, this is the crux of the whole lesson, right? The idea is when one of these linear differential equations is written in this standard form, you can find the integrating factor by doing this operation. Okay, the integrating factor for a first-order linear differential equation is going to be e to the integral of p of x dx. And so what we effectively need to do is we need to take any differential equation we have, we need to put it in standard form, we need to find p of x, which is the thing in front of y, and then we need to do this computation. We need to do the integral of that p of x and then raise e to that power. And so before we just dive straight into a problem, I want to just do those first few steps. So in this next example, I want us to take a moment to write this thing in its standard form, identify what p of x is, and then find the integrating factor. If you're feeling bold and want to try this on your own, go ahead and pause the video and do so. The things I would remind you about the standard form is that the standard form has y prime alone, it has some function of x instead of y, and everything else is over on the other side. And so that's really what you want to be going for when you're trying to put this thing in standard form. So, if you've tried this on your own and you want to take a look at it for yourself, remember the key thing here is y prime is supposed to be by itself. So the thing that's keeping y prime from being by itself is that we've got this x that's in front of it. So the step that I'm going to take to getting y prime alone is going to be divide the problem through by x. So when I divide everything by x, I'm going to get y prime plus, now this next term, I could write this as y over x, but instead I'm going to write 1 over x times y. And the reason is I want this thing, 1 over x times y, to look like p of x times y. And then this will be equal to, now over here, I need to divide the other side by x as well. Over here, I just want to have q of x. So I'm just going to make this 1 over x cubed. Okay, at this point, we're in standard form. I now have y prime. Here I have p of x y, and over here I have q of x. So at this point, it should be really clear to us. We can see that p of x is 1 over x, And the last question, the last thing that this example wanted us to do is it wanted us to find that integrating factor. My integrating factor is supposed to be e to the integral of 1 over x dx. Okay, well, the integral of 1 over x is natural log x, so this will be e to the natural log of x plus c. Turns out that plus c is not going to matter, but I'm going to sort of share with you why in just a moment. We've seen this enough times now, right? We know that this becomes ce to the ln x. And then remember, e to the ln x can actually be simplified, and I'm going to get cx. So my integrating factor in this problem is going to be cx. It's actually just going to be x, but I'm going to leave it to the next slide for us to sort of talk about why it's just going to be x. All right, so now that we've gone through this first few steps, we figured out how to write it in standard form and how to find the integrating factor. I want us to go through the solution for this whole problem. And so, we're using the exact same thing that we just did. And so these first few steps are going to be really quick. The first step in working through these differential equations is going to be to write it in standard form. So if you recall from the previous problem, this for us was y prime plus 1 over x y equals 1 over x cubed. Okay, that was our standard form. We divided through by x, we got that thing. The next step for us was finding the integrating factor. Remember that we did that by identifying that p of x was that 1 over x, and then we did e to the integral 1 over x dx. And remember, we did all this work like 1 minute ago. We recall that the integrating factor was cx. Okay, now, I mentioned in the previous slide that c isn't really going to matter, and I'm going to show you right here why it doesn't matter. Okay, so the next step here is that we're supposed to take this integrating factor that we have and multiply it through the differential equation. So we're going to take our standard form differential equation, and I'm going to multiply that through by that cx integrating factor. So when I do that, I'm going to get cx y prime plus cx times 1 over x is just going to give me cy equals, and then cx times 1 over x cubed is going to give me c over x squared. So do you see now why we didn't need the c? Because I'm multiplying through the whole problem by this thing, that constant that's there is always just going to drop out, right? So when I multiply through by the integrating factor, what I'm really going to end up with here is x y prime plus y equals 1 over x squared. Now, the next step is really the magic step, right? If you have done all of your work correctly so far, when you get to this next step, the left-hand side of this thing right here, is something really pretty magical. It turns out that that thing is the product rule of something. That thing is the product rule applied to y times x. And if you don't believe me, try it out for yourself. If you were asked to take the derivative of y times x, you would do the product rule on it. You would take the derivative of y, which is y prime, and you would leave the x alone, and then you would add. Then this time you would take the derivative of x, which is 1, and you leave the y alone. This is exactly how first-order linear differential equations work. You find the integrating factor, you multiply it through the problem, and the result that you get, the left-hand side, will always be the product rule of y times the integrating factor. Well, I mean, the integrating factor without the c, and we're actually going to stop writing the c from this point forward because it doesn't matter, okay? So the left-hand side is the derivative of y times x, and the right-hand side is still this 1 over x squared. But the amazing part is at this point, we now have a simple differential equation that can be solved. Since the left-hand side has been expressed as a simple derivative and the right-hand side is a basic function, right? All I have to do is integrate both sides. So if I take the integral of both sides of this thing, on the left-hand side, the integral and the derivative basically cancel out. I'm left with yx. On the right-hand side, I'm going to have the integral of 1 over x squared. Okay, we'll increase the power to -1, divide by that thing. This is going to be -1 over x plus c. And I mean, we could be done here if we wanted to. I mean, that's effectively an answer. Lots of times we like to get y alone, and so when I say rewrite if necessary, if the problem indicates that they want it to be in terms of y or they want it to have some certain form, make sure that you answer it that way. If we wanted to solve for y here, it would just mean I'd divide through by x, and I'd get negative 1 over x squared plus c over x. And this is the other potential answer for us. This is the process for solving these differential equations. Okay, we write them in standard form, we find the integrating factor, we multiply through by that integrating factor, and when we do that, the left side will be like rewritable as a product rule of y times the integrating factor. Then you integrate both sides to wind up with your general solution, and then rewrite if necessary. I wanted to put this up on the screen at some point. I'm not going to actually go through all of these steps again because I just talked about them. But in case you wanted to sort of see at a glance really quickly what the steps were for solving a first order linear differential equation, here they are. We're going to go through another example now. This next example is likely to be a little bit more complicated. I'd encourage you to go through the steps one at a time. And if you want, pause the video and bounce back and just check in to make sure that you're doing it correctly. So the first step here is going to be to write it in standard form. So standard form for us means that we want it to be y prime plus p of x y equals q of x. Right? So I'm noticing that this y term is on the wrong side and this like q of x term is on the wrong side. So my standard form for this is going to be y prime minus, and I'm going to write tangent x times y just so I can really clearly see what that p of x is, equals 1. I've now got this in standard form, and I can tell that p of x is negative tangent x. Okay? So now for the integrating factor, integrating factor here is supposed to be e to the integral of negative tangent x dx. Okay? Now, my integral of tangent is supposed to be negative natural log cosine. So we're going to wind up here with e to the positive natural log cosine x plus c. Okay? Remember, we've worked with this before. That c is going to come down to the front, in front of the e. So we'll get c e to the natural log cosine x. But we also know that e and the natural log are going to cancel out. So we're basically going to wind up with c cosine x. But we're also aware from some of our previous slides that this c really isn't going to matter. The integrating factor for us is just going to be cosine x because once we multiply through by this thing, the c is going to drop out anyway. So my integrating factor here is cosine x. Next step, I'm supposed to take that integrating factor and I'm supposed to multiply it through the standard form of the differential equation. So I'm now going to have cosine x times y prime minus, when I do cosine times tangent, tangent is sine over cosine, those cosines are going to cancel, I'll wind up with sine x times y equals, and this is really important, make sure you don't forget to multiply that integrating factor over to the right-hand side as well. So you're also going to get equals cosine x here. And the next step is sort of the magic step, so make sure that you give yourself a chance to sort of see this next step and make sure that you understand it. It says recognize and rewrite. I don't want people to just rewrite it and not think about it. I want you to recognize that this really is what's happening. It's supposed to be the derivative of y times the integrating factor. And what I personally always do here is I stop and think, did this really work? Did I do this properly? When I do the derivative of this, am I really going to get this back? The derivative of y would be y prime, and I'd leave cosine x alone, plus, that's a minus, so something's got to come back to that later. Now I would leave the y alone, and the derivative of cosine would be negative sine. That's why there's a negative there. We sort of get to see, hey, this thing really is the result of the product rule applied to this. On the right-hand side, I'm just writing cosine x. Okay? Now that I've gotten through that step, my next step is to integrate both sides of this equation that I have. On the left-hand side, the integral and the derivative, cancel one another out. I'm left with y cosine x. On the right-hand side, I get the integral of cosine x, which is going to be sine x plus c. And then, as we'd mentioned before, this is an acceptable answer. That like we can be done with it right there. But if your problem, for instance, said that they wanted you to write your answer, in the form y equals f of x, all right, well, we would need to solve for y. So if I wanted to solve for y here, we would have y equals dividing the cosine through tangent x plus, I could write c over cosine, or I could write c secant x. And this is another acceptable version, acceptable writing of the answer for this differential equation. This is always going to be the process for first-order linear differential equations. You'll notice that this is a lot less sort of algebraically intense than homogeneous differential equations are. So first-order linear differential equations tend to be, pretty straightforward. They are linear. So have a good one, everybody.